this video, we are going to look into some of the fundamental and important concepts of quantum mechanics. Apart from the concepts, methods, and mathematical interpretations, this video is super important for you because I would be explaining some of the deep fundamental rules and nature of quantum mechanics. So for those who are learning quantum mechanics or those who are willing to learn or who are already into the system, this video is very important, and I would request not to skip any part of this video because each of these parts are intricately related to each other. If you miss one part, you will be missing on the second. So this video will contain some of the basic core fundamental methods and concepts of learning quantum mechanics so that the future of learning quantum physics becomes easy for you. My name is Shaunak and you're watching this video on my channel Physics for Students. Season's greetings and a warm welcome. Before we go ahead in understanding what are the details that we are going to cover, first let us understand what are the topics that we are covering. We will be first covering the most important thing, that from classical system to quantum system, what is the core and the key difference? What is the probabilistic nature of quantum mechanics? The superposition, what actually is a classical system? What are the different systems and experiments and how the quantum nature of the experiment changes? What is a wave function? The statistical interpretation, what is probability, probability density, and then we will summarize our learning. These are the topics to cover, and it is a good time that we can go ahead. The first of all, what we need to understand that in physics, classical mechanics and quantum mechanics are two major subfields of mechanics. Classical mechanics is concerned with the set of physical laws describing the motion of bodies under the action of system of forces. Now, classical physics is causal. Complete knowledge of the past allows computation of the future. Likewise, complete knowledge of the future also precisely helps us to compute the past. Now, here there is a paradigm shift. Now, what we mean by paradigm shift, let me explain it to you. So, when we are into the classical world, I mean to say Newtonian or pre-Newtonian, we are now moving into a quantum world. So, there is a complete shift in our thinking. We are into a deterministic world where position and momentum are initial conditions. Once it is given, we can definitely find the future, but now we are going into a probabilistic world. The world of certainty is now being replaced by uncertainty, and the common sense, what we generally perceive the world by common sense, things move around, fall around, electric charges, etc., are now devoid of common sense. That means we are moving into a world where these common sense are no longer valid. Taken all these things into account, what we are now encountering is called a paradigm shift. And that is why I just wanted to tell you at the beginning of the video that we are undergoing a paradigm shift, both in terms of common sense, general knowledge, and the mathematics. So the probabilistic nature. Now, the quantum events occurs for no reason at all, no cause. Rather, these tiny objects have what is called a probabilistic distribution that describes their location, momentum, and few other things, such as whether they will spontaneously break up into small things or not. Now, it is impossible to predict that certain outcomes of a single experiment on a quantum system. So what we do is that the only thing that we can predict is the probability. That means whether it will be probably in a position or not. So that is why I have written the discrete possible outcomes of a quantum system. So here is a photon which is going in this direction. If you want to find out that whether it lands on this or this, the two black dots on your screen, so we might get that is a 42% chance it will land up here, and that is a 58% chance it will land up here. Now this is something which really bothered our Dr. Albert Einstein, and in his letter to Max Born, Einstein made a famous a statement that quantum mechanics is very impressive, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but it does not really brings us closer to the secret of the old one. I, at any rate, am convinced that God or he doesn't play dice. Now, Einstein experiments sentiments similar to this on many occasions throughout his life. In various ways, Einstein became fond of insisting that God does not play dice with the universe. So here, as I told you, that this is also a paradigm shift from a deterministic world going into a probabilistic nature of the world. Now, there is also a concept which is called superposition, which is a fundamental principle of quantum mechanics. It states, much like waves in classical physics, any two quantum states can be added together or superposed, and the result will be another valid quantum state. So an electron is simultaneously covering all the locations in its wave function. So here you see that in a classical system, the position should be 0 or 1, whereas in a quantum system, it is both. So if I flip up a coin, right? So when I'm flipping up this coin, right in the air, it is both in head and tail conditions. But when it finally lands down, then we can tell that it is either head or it is tail. So similar thing has been expressed by the famous German physicist Edwin Schrödinger, that the cat is both dead and alive. So this is what is called superposition, or the quantum state is superposed. So mathematically it refers to a property of solutions to the Schrödinger equation. Since the Schrödinger equation is linear, any linear combination of solution will also be a solution. So once we have understood that there is a paradigm shift, there is a superposition, and we are unable to understand where the particular particle is, now it is time that we need to define what is called a classical system. Why we are defining classical system? Because until we define a classical system, we won't be able to know what is a quantum system. Note that classical system does not mean actually the classical mechanics or something more deep. Now, the term classical physics refers to physics before the advent of quantum mechanics. Classical physics includes Newton's equations for the motion of particles, Maxwell and Faraday's theory of electromagnetic fields, and Einstein's general theory of relativity. But it is more than just specific theories or specific phenomena. It is a set of rules, an underlying logic, and a set of principles that governs all the phenomena for which quantum uncertainty is not important. These general rules are called classical mechanics. Now, in classical physics, if you know everything at one point of time about a system at some instant of time, then you can know also the equations that govern the system changes. Then you can predict, which is called the deterministic, and it is also reversible. So I have written it is both deterministic and reversible. So here it is. It can predict the future and how the set of events will behave. So in classical physics, if you know everything about a system at some instant of time, you also know the equations that govern how the system changes. Now, when we're talking of classical system, what do we mean by system? Now, when we talk of generally it is a system, so it can be a point of particles or charges, etc. It can be a magnetic charge or photons or whatever. So in a non-relativistic system, obviously, which is called, it is a closed system, right? So when it is a closed system, so it means that it doesn't exchange any matter with its surrounding, right? And it is not subject to any force. That means not some external force is acting on that. Now, say for example, we could take one coin. Say for example, I have taken a €1 which is glued to a table, right? So in physics, the collection of all those states, these are states occupied by a system, is called space states, right? So it is a space state. The state, so the state space is not an ordinary space. It is a mathematical set whose elements label the possible states of the system. Now here, as you see the coin €1, here the state space consists of one single point, namely heads, which I have mentioned as H, because the system has only one state, right? Now, predicting the future won't be difficult because it will, something external force or nothing is occurring. So nothing ever happens and it always be head. So it is called a one state space, and it is called a single state system. So we have defined what is the system. Now we have defined what is a closed system which doesn't exchange any matter. and we have just taken one coin which is glued to the table. It has got one head which is being shown. It is in a single state system. It has got a state space, and the future just shows that it will only show H. Now, if we want to define something which is called a two-state system, we take a head and a tail, right? Just two abstract objects. Now, in classical mechanics, we assume that systems evolve smoothly, right? That means without jumps or interruption. Such behavior is said to be continuous, right? So yes, in classical systems evolve smoothly, there are no discrete jumps. So obviously you cannot move from heads to tails smoothly, but let us just assume it. So moving in this case not necessarily include discrete jumps. So we assume that the time comes in discrete steps labeled by integers. So here is the head, and so the system that changes, so it goes up to head, and so the future would be what? Head, obviously H. And then we got a tail, and the system moves back to tail. The future would be obviously tail. Now again we take into a system, our old system, a magnetic field, electron and a photon firing each other. So if the system that changes, here is a time now, a system that changes with time is called a dynamical system, right? A dynamical system consists of more than one space of states. It also entails a law of motion, a dynamical law. Anyway, so on a very simple dynamical law is that whatever the state at some instance, the next state is the same. So here we saw that it is the same head, it is only H, and it is only tail. Now, there could be a dynamical system which is opposite. Now, say for example, we get a head and a tail, right? Now, this arrow from head to tail leads to here, and from the tail to head, it leads to here. So we can still predict the future. So if we start with, say for example, head, we assign a value, for example, sigma, which is a positive and a negative. And if we take we start the dynamical systems, and we start it from H, that is the history, and we want to predict the future, it will become head, tail, so on. And if we start with tail as the history, then we obviously get tail, head, something like that. So what happens is that this is something which is called this degree of freedom, which is our coin or anything, and we have denoted it by the Greek letter sigma. So sigma has two possible values, right? Positive for head and negative one for tail. So we can use a symbol, this symbol, to keep a track of the time, right? So degree of freedom is what? It is the number of independent parameters that define its configuration of state. So if we take now that we denote time as t and the number of discrete evolution, remember that in a classical system we're talking of discrete, that is integer, or discrete system without any jump, then we denote it as n. Then what we can do is that we can use head to denote this and tail to denote this. It's simple, right? Sigma of n plus 1 is equals to positive sigma of n, because it is the head and that of the tail. So I think that till now it is clear. Now what we do is that there are other ways in which we can define a dynamical system. Say for example, we take a cube, right? I've just shown those 6 parts. Now what we can do is that we can say we can go from 1 to 2, then we can go from 2 to 3, and then we can go from 3 to 4, and 4 to 5, and 5 to 6, and 6 to back to 1. So what happens is that this works absolutely fine. I mean to say, we go from one state to another and to another. So such pattern, so now we take, this is called dynamical law 1, and then we take a little bit of complex system, something like this, right? So it has got the arrows, it is a little bit a complex system. So we call it dynamical law 2. So now what you see is that we have what we call the 6 possible states, and this is called a 6-state system. So 1 state, 2 states, so on, and we have got a 6-state system, just to let you know how things really happen. Now, according to the rule of classical physics, not all laws are really legal. I mean to say, not all laws will work out. So it is not enough for a dynamical law to be deterministic, it also has to be reversible. Now, what do we mean by reversible? Let us see. So this is 1, where from 1 we are going to 2, right? From 2 we can go to 3, right? So if at 3 we can go back to 2, and there is no ambiguity for the future. So the arrows are reversed, that means it is deterministic. So now if we take the same figure, okay, we are going with the same figure, and suppose I'm standing at 2, right? Suppose we are at 2. Question is that where were you just before that? Before 2, where were you? So you could have come from here, that is from 3 to 2, or you would have come from 1 to 2. So, right? So the diagram actually doesn't tell you. Even you see that in terms of reversibility, there is no state that leads to 1. That means state 1 has no past. That means if the question mark is that I cannot go from here to here. This is not allowed, right? So state 1 has no past. So that is why we call that meaning of reversible in terms of physics can be described as the most concise description would be that if you reverse all the arrows, right, the resulting law is still deterministic, right? So another way is to say that the laws are deterministic into the past as well as the future. So here you see on the right hand side I've written there must be one arrow to tell where you are going and one to tell where you came from. Now this system is what is called, it is a irreversible system. It illustrates just the kind of situation that is prohibited by the laws of physics. So here finally I have written that state 1 has no past and there is no state which can lead back to 1. So this is a concept which is again very important, reversible and irreversible system. Okay. Now we will see something which we have gone from one place to another, but now we will see a kind of a cycle. So if we see 1 and this arrow points back to 1, whereas 2 the arrow points back to 2, and 3 and 4 are just like this. So each cycle has its own dynamical rule, right? But they are all the part of the same state space because they describe the same dynamical system. So state space is separated into several cycles. And each cycle has its own rule, just like 1 and 2 belong to its own cycle and 3 and 4. Now, whenever a dynamical law divides the state space into such separate cycles, there is something which is called a memory in which the cycle actually started. And this memory is called the conservation law. So this memory is called a conservation law. It tells us that something is intact, something has not changed. Now, in order to make the conservative law, what we just stated, that it divides the state space into separate cycles, we give each cycle a numerical value. So 1 plus 1 and minus 1 goes from here to here, and it is 0, right? So that's, we can label these cycles as this q equals to 1, q equals to minus 1, and q equals to 0. So whatever the value of q, it remains the same for all time because the dynamical law does not allow jumping from one cycle to another. What we state is that q remains conserved. So just to tell you once more that when the dynamical law is, you see that it is dividing the space into small separate cycles. There is a memory, that means where they started it, and this is called a conservation law. And when we quantify those with plus, minus and a 0, the value of q remains the same. Okay, so now once we have seen those values and etc., the question comes that can we predict whatever we are telling in terms of experiments? So the question comes that what is really so special about quantum mechanics? I mean to say, you will often see people asking that quantum mechanics is so difficult and is so hard to tell. But actually it is not so, because quantum mechanics deals with the behavior of objects. Say for example, it can be an electromagnetic wave or anything, and it can be a kind of a photon or an electron. It deals with behavior of objects that are so small that we human beings are quite ill-equipped in order to visualize them all. Individual atoms are near the upper end of this scale in terms of size. So what happens is that electrons are frequently used as study for the sake of study, but our sensory organs are simply not built to perceive them. So the best way what we can do is that we can do certain mathematical abstractions in order to understand that. You might say that classical mechanics is also full of abstractions. Newtonian mechanics, point masses, rigid bodies, inertial frames, positions, momentum, field, it goes on. Yes, it is true. There's nothing new about mathematical abstractions. Quantum mechanics, starting with Max Planck, also contains abstractions, but there is a difference. One is that there is something which is called the idea of a state. So there is a different abstractions. So quantum abstractions are fundamentally different from classical ones, because we will see that the idea of state in quantum mechanics is conceptually very, very different from classical mechanics. And the states of measurement in the classical world, the relationship between the state and the system and the result of measurement on that system is very straightforward. In fact, we can call it as trivial, that labels that describe a state, for example, position, momentum of a particle, are the same labels that characterize measurements of that state. So abstractions are same both for classical and for quantum world, but there is a difference in terms of the idea of state and states and measurements. Okay, so what we do is that we take the same head and tail, right? And we try to define them in terms of degrees of freedom. Okay, so for example, if we take this one head equals to +1, then what we find is what is called, it is a qubit. Now this is an old concept, but it's good for us to define right now. So qubit is basically a quantum mechanical system, one of the simplest quantum system displaying the peculiarity of quantum mechanics. It is being termed first by Benjamin Shoemaker. Now, for example, we take examples of the spin of the electron, in which the two levels can be taken as spin up and spin down, or we can consider the polarization of a single photon, in which two states can be taken to be the vertical polarization and horizontal polarization. Now, in classical system, a bit would have to be in the state or the other. However, in quantum mechanics, what happens is that it allows the qubit to be in a coherent superposition of both states simultaneously. I repeat, quantum mechanics allows the qubit to be in coherent superposition of both states simultaneously, a property that is very fundamental to quantum mechanics and quantum computing. So now if we take the discrete instant as n and the next as n+1, then definitely we can define this. So we can define definitely as this. Okay, so this is what we define as qubit. And why we define qubit? Because we need a 1 and a minus. Now here we would like to go ahead with an experiment, and this is very core, so I would request the viewers to pay good attention, because this is something very central. Now here is an apparatus, right? It would record the results of the measurement. I have taken a spin. In case this is of the two-state system, the apparatus interacts with the spin and records the value, which is sigma. We will come to that. You can think of the apparatus as a box with a window that displays the result of measurement. Now it is question mark. So before the apparatus interacts with the spin, the up arrow, remember, it is important because it shows how the apparatus is oriented in space, right? And its direction will affect the outcomes of our measurements. So we begin by pointing it along the z-axis, which I have already given. And initially we have no knowledge whether sigma will be plus or 1. So that is why I have put a question mark. Now after the interaction, so our purpose is to perform an experiment and find out sigma. So once this interacts, so we are measuring it in x, y and z axis, and once it is measured, the spin with the apparatus, what we find is that it is a +1, right? So after measurement, it shows that it is a +1. So now the thing is that if we reset the apparatus to neutral, that means we reset everything, and yet we get the same result, that is +1. So that is how the window shows a +1 or a -1. Sigma is either +1 or -1. Okay. So what we do next is that we do something new. Okay. So after preparing the spin up, we turn the apparatus upside down. So we actually flip it, right? 180 degrees. Apparatus is upside down. And then we measure the sigma again. The XYZ remains the same. So after the apparatus has been flipped, the new measurement shows sigma equals to -1. Right? The upside down apparatus records sigma equals to -1. Similarly, if you originally prepared to -1, then it will come to +1. We will see that. So if the apparatus has been prepared sigma equals to +1, it would go to -1. If you prepared -1, the flipping would produce +1. So from these results, we conclude that sigma is a degree of freedom that is associated with a sense of direction in space. Right? So it is a degree of freedom and it moves according to the direction of space. Now we have, put it totally upside or flipped it 180 degrees. Okay. So if that is so, I mean to say, in the previous slide you saw that if it is a degree, it is a degree of freedom, then we can say that sigma is a kind of a vector, right? Then it would be natural to expect that tuning in the apparatus over would be reversibility. Obviously, flipping the apparatus would read sigma z equals to -1. So we can consider these to be something like our typical components of a vector, sigma x, sigma y, and sigma z. So if we are convinced that the spin is a vector, for example, this sigma 1, and we would naturally describe it by three components, sigma x, sigma y, sigma z. So when the apparatus is upright along the z-axis, it is positioned in the sigma z direction. Okay. Now we do something totally different, right? Now what we do is that we rotate the apparatus around 90 degrees. Okay. So it's for some pi2 radians. Now the apparatus begins in the upright position. A spin is prepared. Okay. So we see this step by step. We start with a spin of +1, +1. Next we rotate it. So the apparatus rotates to 90 degree. We then measure the sigma x, right? And what is that? Sigma x has to be 0. But it is wrong. It shows it is either +1 or a -1. Okay. So now the question is that in fact sigma actually represents a component of a vector y, because initially we confirmed, if you see in the previous slide, that sigma was directed along the z-axis, suggesting that obviously in the x-axis it would be 0, but to our surprise we get sigma x, the apparatus gives +1 or -1. So what it happens, it refuses to give an answer other than I would say ±1. If the spin really is a vector, it is very something which is very peculiar, you understand, because it has to be in the direction of x spinning up in this 90 degrees, then it has to be 0. If we take that sigma really operates as a vector with its component, but it shows either +1 and -1, and that is something very peculiar. Okay, so what I'm trying to tell is that if the apparatus is 90 degree, we begin at the x-axis, +1, rotating the apparatus around the x-axis. If we measure that, and if we repeat the same experiment number of times, then obviously it leads to a statistical result which is +1 or -1, and the repeated experiment randomly produces what is called a ± kind of thing. So the average value of sigma, although it comes to 0, which actually saves our day, but that is how things are. So this is something really weird. So you can understand that systems and experiments, how things are changing. Okay, now what we do is that we take this apparatus and we just rotate it in any kind of an arbitrary direction along the unit vector. When we are rotating along in an arbitrary direction, what happens is that we get a kind of this vector, this unit vector m and n, and we get a kind of a theta. So the components of theta along the n-axis, now if n lies at an angle theta with respect to the classical answer, so the classical answer should be sigma is equal to cos theta. But as you might guess, each time we do the experiment, again we get sigma equals to +1 or -1. However, the result is statistically biased so that the average would be something equals to cos theta. So we pick the apparatus again. We can pick it in M. Apparatus should be +1. We rotate the apparatus and that is the result that we are getting. So the repeated experiments produce a random kind of a plus minus result. Okay, so quantum mechanics, this is the notation for the statistical average. We call it Dirac bracket notation. So we may summarize that the results of our experimental investigation, if we begin with the apparatus oriented along the M and confirm that that sigma is +1, then subsequent measurements with the apparatus along the n-axis gives the statistical result n dot of M. So if you start with the apparatus oriented with M, we set the spin sigma equals to +1, and the apparatus oriented N with given the statistical result is n dot M. So what we find is that we are learning that quantum mechanical systems are not deterministic. You see, it yields to certain other results. We are expecting either a 0, it gives plus or minus 1 or something like that. The results of experiments can be statistically random, but if we repeat an experiment many times, what we get is that the average quantities can follow the expectation of classical physics, and that saves our day. So up till now, I believe that things are quite clear for you. The system and experiments, this part actually shows that the quantum mechanical systems are not deterministic. With the rotation of the apparatus and the outcome that results, although the average quantities follow the expectation of classical physics, yet these are not deterministic. So we now come to the central part of quantum mechanics, and that is what is called a wave function, right? So we can explain a wave function again starting with comparison, which will be easier for classical mechanics, and we get a point which is determined by a position and time, and we can get a coordinate like 2 and 4. But in case of a quantum system, if we get this kind of a wave, then we can say an electron or subatomic particle can be here, can be here, can be here. It is not sure. It can be any one of this position. So that wave function is denoted by the Greek letter psi, and it denotes a variable quantity that mathematically describes the wave characteristic of the particle. So the value of the wave function at a particular point gives a point of space and time, and its likelihood that it might happen that the particle is over there. We will soon see a mathematical interpretation which will make us easy, and the probability of finding is done by squaring the wave function that is squared. So actually psi doesn't have any physical significance when evaluated at a particular point of time. This denotes it should be multiplied by its complex conjugate, and this one is that we need to do a normalization, and when we yield a value of 1, it is the particle has to be somewhere 0 or 1. So wave function is defined to be a function which describes the probability of a particle's quantum state. A wave function can also be described that the probability of finding the electron in a matter wave, its squares leads to a real number solution, and the probability of an electron being within a certain area once it is squared can be assessed. Okay, so what exactly is the wave function and what does it do for once you have got it? So after a particle, you understand by its nature is localized to a point, whereas the wave function, as the name suggests, it is spread out. It is like a wave of a sea. So we see that this kind of a function, right, is a function of x for any given time. So how can such object describe the state of a particle? The answer is given by Max Born's statistical interpretation of a function, which says that this one actually psi x t square dx gives the probability of finding the particle at a point x at a time t, or more precisely this one. Right. So the probability of finding the particle between x and dx at a time t. Now let us take this one x and this one psi square, and let us draw a kind of a wave like this, right? So what happens is that A, B and C, and this is the area where there is a probability, the circled one, that is the probability of finding the particle is more around A rather than B or C. So the wave function, you could likely find the particle in the vicinity of A and less relatively finding the particle near B. So you see that statistical interpretation introduces a kind of an indeterminacy into quantum mechanics. Or even if you know everything the theory has to tell you about that, really don't know. So here actually this Max Born's statistical interpretation shows the indeterminacy but the probability of finding the particle. Now suppose I do measure the particle and I find it to be at C. So let us draw it again, right? And suppose we find it at C. Now, where was the particle just before I made the measurement? So here it is C. So suppose we find it at C. The question is that where was the particle just before I made the measurement? Now there are three plausible answers which I would just like to make a quick note, although they are not mathematical, but it's quite good. The first one, which the realist would say, is that the particle was at C. This, seems like a sensible response, and it is the Einstein's favorite, that if this is true, then quantum mechanics is incomplete theory, right? Since the particle really was at C, and yet quantum mechanics tells that it was unable to tell. So to the realist, indeterminacy is not a fact of nature, but a reflection of our ignorance. Okay. So part 2 is that the particle was not really anywhere. It was the act of measurement that forced the particle to take a stand, right? So this is something which is a view of the so-called Copenhagen interpretation. It is associated with Bohr and his followers. And the third one is that agnostics would refuse to answer, right? Now, because we are dealing more with statistics and interpretation, this is a kind of an idea that how the statistical interpretation would do. But let us take a quick look into a very simple example of probability, which will make things clear. Now, suppose that we are inside a room, okay? Because why I'm saying, because probability plays a central role in quantum mechanics. So, and there are 1, 2, 3, further. So you can count it, there are around 14 people whose ages are this. So one person 14 years, one person 15 years, and so on. And if we let nj represent the number of people and age as j, then we get something like this, right? So can we compute the total number of people of the room? I mean, the total number of people in the room, then we can, so we can calculate this, right? So this is just an example to show that how probability really happens. Okay. Now, see, what happened is that till now we have only taken discrete values. That means isolated values, right? That one can take an isolated value. So it has to be integer or something. But it is simple enough to generalize this discrete value into something which is called a continuous distribution. So, for example, on the road there are these people who are standing, right? These people are standing. And I want to select them randomly. And I want to select them randomly in terms of their age. And I want an age which is 41 years, 25 minutes and 2.55555 seconds, right? Something like that. The only sensible thing that we can do is that we are not going to get this. Probability is absolutely zero. So what we can do is that the sensible part is that we speak about the probability of their ages lies in some interval between certain and certain times. So here is an interval which we are speaking as 41 years to 41 years 2 days. Now if the interval is very, very short, right? If the interval is sufficiently short, this probability is proportional to the length of the interval. Now for example, that the age is between 41 years to 41 years 2 days, right? So what we can do is that we can say from here that we are talking of a very infinitesimal small interval. Then the probability that an individual chooses at random which lies between x and x plus dx is this one. And this rho, this proportionality factor, this is actually called the probability of getting x, the chance. But we use it in a better term which is called probability density. The probability density that x lies between, A and B, we will look at now. If it is A and B is something like this. And this is what actually tells that the probability that x lies between A and B, which is a kind of a finite interval. So this is the way in which we take the probability factors, we select random thing, and how we can find it. Okay, so we have seen this equation, right? So it tells that the probability density for finding the particle at a point x and at a time t is given by this. However, it leads to some other important concepts. Normalization, complex number, vector spaces, bra and ket, momentum, and the uncertainty principle, which will be covered in the next video. So these are the concepts which obviously are central to quantum mechanics, but we will take a pause to this video right now, and we are going to find it in the next part of the video. So let us time to summarize. So we learned between the difference between classical and quantum system. What is a quantum system and what is a classical system? We've understood it with a lot of examples. The probabilistic world, how it behaves, what is a superposition. We saw certain systems and we experimented those systems with spin and turning 180 degrees, 90 degrees, arbitrary, and we found that the behavior of the systems are quite weird, and from that we found out the conclusion that quantum mechanics is not deterministic. We found wave function, probability, and probability density. That's it for this part of the video. As I have shown, I will be covering the next part in the next video. Do let me know your comment. Do let me know your opinion. Please subscribe to Physics for Students. Click on the bell notification and click on all to get all the notification from Physics for Students. Thank you very much for watching this video. The Christmas is coming. Season is now full of flowers and festive. I hope you're enjoying wherever you're there in any part of the world. And my best wishes and season's greetings is being conveyed right now. Wishing you all the best and a Merry Christmas. Before that, we will come up with few more videos. Till then, goodbye and stay happy.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.